Okay, so
How was handing you a cookie? Everyone dropped it. You like fumbled with it for like a whole minute.
That was ridiculous. If I didn't catch that, I would have been.
today we're going to continue on with our integration work. Right now you have a pretty firm grasp on the mechanics of taking an antiderivative, aka integral. Today we're going to talk about a little bit of theory. So you'll recall that when we did derivatives, we had three explanations for what a derivative was. And those three things were: a derivative is slope of, that's right?
Tangent line?
Slope of the tangent line to the curve. Good. No.
Velocity.
Velocity and that other thing.
Rate of change.
Rate of change. Very good. Same thing is true with integrals. There is a physical representation of the integral, but there's only one of them, and it is area. Okay, so we're going to look at this simple thing. Understand the concept of area and the fact that the integral represents the area under the curve. We're going to do some approximations for some areas, and we're going to use some limits, but probably not too much of that because that's scary and ugly. And then hopefully you've been practicing on drawing your squiggly integration symbol so it doesn't look silly. How many people think they have that under control? Awesome. How many people think they've perfected it? Really?
That's a lot of confidence.
Let's
Prove it.
It's a bold statement right now.
Yeah, bold on the board. We'll see how this one plays out.
Hold on.
You can make me use that.
Yeah, because now it's on. Then it's on the video.
There's no way that you actually.
Oh, that's a little bit. Hold on.
How many shots are you getting? It's not horrible. Let's keep it up, huh? Not bad. Okay, so simple concept today that's going to get complicated because there's 4 different ways to do it. It's going to get a little weird, but roll with it. Okay, so like I said, I explained this already. Derivatives had 3 different things. Integrals have one thing. It's the area under a curve. That curve being your function. And the examples that I have today all involve a parabola, but it doesn't have to be a parabola. It could be any function. It's the area under the curve. In other words, the area between the curve and the x-axis. What's up, slacker? You're sorry about being a slacker?
I guess.
Okay. Here we go. Here's a little function. So that red line is my function. I don't know what it is. Could be part of a parabola. Could be a lot of different things. And I took that function from, let's say, 0 over to this value over here, which I can't even read, which is irrelevant, and I split it into rectangles. Now, why rectangles? Well, we're not just going to do rectangles, but we're going to start with rectangles. Right now, I don't have an accurate way to find the area under the curve. That comes later. What we're doing now is an approximation. Notice it says approximating the area of the plane region. So I split this region into 5 rectangles. Why 5 rectangles? Because that's what the problem asked for, 5 rectangles. And I have 5 rectangles that go from 0 to 10, so therefore how wide is each rectangle? 2. How'd you get that? How's it okay?
10 divided by 5.
10 divided by 5. What if I went from 2 to 30 with 5 rectangles? In other words, not every function is going to start at 0 and end at 10. It's not always going to divide nicely. So we need a formula. By the way, the width of these rectangles is called delta x, change in x. We need a nice formula to find the width of each of those rectangles, and so we get this little guy. B minus A divided by N. Now what does that mean? B is your ending point, A is your starting point, N is the number of rectangles that you need. So if we go back to the example where I said 2 to 30 for, what did I say, 5 rectangles?
Yeah.
2 to 30 would be 30 minus 2 is 28 divided by 5, so each rectangle will be 28/5 wide.
A is your endpoint.
Left endpoint, yeah. B is the right endpoint, A is the left endpoint, N is the number of rectangles. Got it, man? Does that answer your question? Okay. You'll notice, however, that when I've got these 5 rectangles, I've got a bunch of wasted space. See all this white space between the purple, what are these shapes? Rectangles. Between the purple rectangles and the curve, I've got a bunch of wasted space. That's why it's an approximation. So the first question is, how could I make my answer more accurate?
Use more rectangles.
Use more rectangles. Or,
Make them skinnier
yeah,
rectangles.
same result. Skinnier rectangles or more rectangles will give us a more accurate answer. And I have a demo for that in a second. Okay. So this thing that I have illustrated here is what's called left-hand rectangles, meaning I drew my rectangles and then I came up on the left-hand side, and when I hit the function, I came across. Okay, so up on the left, come across. 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 Okay, so that's the first of the 4 different areas we're going to use. Okay. Similar picture there. So left-hand rectangle. Now this is a little bit different because my curve is different. So notice some of these left-hand rectangles are below the curve. Some of these left-hand rectangles are above the curve. And I'll show you how to do this later. But you can see when the curve goes from decreasing to increasing, the types of rectangles change. And so illustrating what we just talked about, if I want a more accurate answer, I can increase the number of rectangles. And you see if n gets large enough, then we would get a more accurate answer. How large do we want n to be, theoretically? Infinity. We want an infinite number of rectangles, and we'll deal with that later. Today's stuff is just going to be a nice, easy, finite number of rectangles. 3, 4, 5 at most. Okay, so those are left-hand rectangles. If I drag this to the other side, there we go. Yeah, it flips over now to right-hand rectangles, and it changes its color. So now I'm going up the right-hand side, hit the rectangle, or hit the function, come across. Right-hand side, hit the function, come across. So we got left-hand rectangles and right-hand rectangles. We good so far? Yes, sir.
Are we going to be using both?
You bet. In fact, we're using 4. There's 2 other types. Now, how tall are these rectangles? Well, they're all going to be the same width because we determined that, in this case, delta x is 2. That's why my 2 is out in front here. How do you find the area of a rectangle? It's width times height. Well, we know the width is 2. How do I find the height? Well, the height is the height of the rectangle when you get up to the function. So notice this first rectangle is, its height is f of 0. Why 0? Because that's the value that I'm on the left-hand side. If I take, let's say, this rectangle, that rectangle has the same width we've talked about, because all these rectangles are going to be the same width. And its height is that distance. Well, what's that distance? That's f of 6. Does that make sense? Now, you could write a formula for all these things like I have up here. The way I like to operate is I just do the geometry. I find the area of each rectangle. When I get all the rectangles, I add them up. I'm done. Okay, so just going across. This rectangle is 2 by f of 0. This rectangle is 2 by f of 2. This rectangle is 2 by f of 4, 2 by f of 6, 2 by f of 10. Does that make sense? Yeah, good. Right-hand rectangles, like I talked about, same thing, just on the other side. So this rectangle now is 2 times f of 2. So the first one is f of 2 because that's where we're hitting the function on the right-hand side. Add all those things up, you got the area under the curve. Notice that on the left-hand rectangles, in this particular function, we have wasted space below the curve. So this is what's called an underestimate. The answer for the area will be less than the actual area. On the right-hand rectangles, we have what's called an overestimate. There's wasted space above the function, so it will be bigger than the actual answer. That's not always going to be the case depending on the shape of the curve. So you can imagine if that curve is, let's say, concave down and decreasing, you'd have some different scenarios, and that's why the picture is going to be important, Craig.
I'm just confused on what the difference between the left and right side of the rectangle.
Can you wait a second until I do an example, and then you'll see if I started from scratch, it'll be a little clearer. Okay. Anything else before I move on? Okay. Don't make this more complicated than it needs to be. Draw a good picture and just calculate the area of rectangles. That's it. Here.
Do you calculate the area of the rectangles the same way for left-hand, right-hand rectangles?
Yes, you just use a different height. Got it.
You still use the same thing to find delta x, correct?
b minus a divided by n.
Yeah.
Okay, so let's use this as an example. In this case, I gave you the function because it'll make our lives a lot easier. Question?
Yeah, so which one, B is the right-hand endpoint and A is the left-hand? Okay.
Because we want, and it doesn't matter, it's just going to be, if you switch it, you're just going to get a negative answer, so just take the absolute value.
Okay.
Yeah. If you go backwards, you'd have 0 minus 10 over 5 versus 10 minus 0 over 5. I think I said that right.
Okay.
Okay. So, we'll do the first one in red. I have a function. This function is 1/2 x squared plus 2, and I want to do 3 rectangles over the interval from 1 to 4. So first things first, it's fairly obvious in this problem, but we're going to do the calculation. I want to know delta x. Well, b is 4, a is 1, and I need 3 rectangles. So conveniently enough, each rectangle will be 1 unit wide. We'll do left hand first. So I'll underline this in blue, because this will be the blue scenario. Starting at 1. So 1's over here. 1, 2, 3, 4. Here's the easiest way to do it. I just start, we're going, delta x is 1, so I'm going to draw a vertical line at 1, 2, 3, and 4. Start my problem. Now we're doing left-hand rectangles first. So here's my first rectangle right here. I need to go up the left-hand side. Once I hit the function, I come across. So there's my first rectangle. Second rectangle, going up for 2, hit the function, come across. There's my second rectangle. Up to 3, come across. There's my third rectangle. You with me so far? Good. Then all I do is find the area of those rectangles. So let's start with this first rectangle. How wide is that rectangle? 1, because that's delta x. How tall is that rectangle? Well, which one do I want? Do I want f of 1 or f of 2? I want f of 1. So what is f of 1? It's got it right up there. So that would be 5/2. So this first rectangle, we'll call it Roman numeral I. So the area of I would be 1 times 5/2, which would be 5/2. Then we'll do rectangle 2. How wide is rectangle 2? 1, because they're all 1. How tall is rectangle 2? F of 2 or f of 3? F of 2, because we're coming up the left-hand side. So f of 2 is 4 divided by 2 is 6. So the area of rectangle 2 is 1 times 6, which is 6. And then last but not least, the area of rectangle 3, this guy, 1, 2, 3, still has a width of 1, because we fixed it that way. How tall is it? F of 3 or f of 4? F of 3. What's f of 3? That's 9/2 plus 2. 13/2. So the area total would be 12, 25, 30 halves, 15, I think, if I did my math correctly. No. Units squared, if you like. Doesn't really matter. It's not relevant. Okay? Any problems? Good. So now let's do the right hand on the same picture. Switching colors here. I'm going to start all over again. So I would do my vertical lines first. And now I'm doing a right-hand rectangle. So I come up, I'm doing rectangle 1 now. I come up the right-hand side, hit the function, come across. Now I'm above the function because of the shape of the curve. Come up to here, go across. Come up to here, go across. Question?
For the area of the second one, how did you get 6?
F of 2 is, it should be 4, shouldn't it? Whoops. I could fix that. Good catch. Erasing is a wonderful tool here. Okay, so this should be 4, right? So then, let's see, what do we got?
13.
13? Okay, good. All right, getting back to the red now. Still has a width of 1, so the area of rectangle number 1, or Roman numeral 1, would be, now I'm coming up the right-hand side, so I need f of 2, which is what I screwed up before, but that would be 4 still, right? Area of rectangle 2. Now I'm doing f of 3 times 1. I did that already. That's 13 halves. Yep. And then rectangle 3. This guy has a height of f of 4. F of 4 is 16, 8, 10. Yes? And then the total would be all of those added up. 23, 31 halves.
41?
Did I add wrong?
41.
33, 4, yeah, 41 halves. What do we know about the actual area under the curve? That exact area under the curve, if I was to draw that, it would be this funky shaped thing. What can you tell me about the area of this green region? Yep.
It's greater than 13 but less than 41 halves.
Perfect. Okay. That's not always going to be the case. It depends on the shape of the curve, and that's why a graph is very important, so you can see is that function increasing or decreasing. And we'll talk about how increasing and decreasing affects the rectangles later on after you get used to finding the area of these guys. Okay, so that's the first two types, left hand and right hand. Are we good? Awesome. Clear this out. Yeah, we did that already. Oh, I did. Okay. So the left-handed rectangle. Yes, sir.
So does that just give you the region of what it's like approximating to?
That's an approximation of the area under the curve. Right. Eventually, we're going to get a method that gives us the exact area, but for now, we're just ballparking it. Okay. The last two, the third and the fourth method, are what's called circumscribed and inscribed, or sometimes called lower sum and upper sum. What that means is, you'll notice if we go back to the other slides, that sometimes the rectangles were below the curve, and sometimes the rectangles were above the curve. So for instance, over here on the left, I drew the rectangles so that they are always below the curve. Okay, that's called an inscribed, or lower limit, aka inscribed rectangles. It doesn't matter left or right hand, because notice this one, for instance, that rectangle is a left-hand rectangle, whereas this one is a right-hand rectangle. So you forget about left and right, you just draw your rectangles to guarantee it stays below the curve. Upper sums are the opposite. You draw your rectangle to guarantee it stays above the curve. And then this is what we just talked about. This is what Jimmy mentioned. The actual area under the curve has got to be less than one, but greater than the other. Okay, so it's a different method of approaching these types of problems. And what changes is how you draw the curve. Okay, so again, on the left-hand side is the inscribed circle, or inscribed rectangles below the curve. Right-hand side is the circumscribed rectangles above the curve. And I was going to do this one again, but I thought of something different, and I'm going to make up a different curve here to go through this quickly. Instead of this, let me go to a blank slide. Whoops. Come on. There we go. Okay, so let's do, let's try something like x cubed plus 3. So y equals x cubed plus 3. All right, so get out your calculators for me, please. I'm going to need some help here. I'm just kind of winging this. If I chose my curve correctly, that should be a cubic that's moved up 3 units, right? So it looks something like that. Is that good? Beautiful. Okay. And we're going to go from -1 to 3. And we'll keep it easy and we'll do 4 rectangles. So 4 rectangles. Therefore, what's delta x? 1. Good, that's why I kept it nice and easy. 3 minus negative 1 is 4, divided by 4 rectangles gives me delta x being 1. Okay. And we'll start with inscribed rectangles. So when you do the inscribed rectangles, you're still going to use the same method. My graph is off a little bit here. Not drawn to scale. Same method I used before. So from each of the points, I'm going to extend a line up to the curve. Okay, this negative 1 should be over a little bit more. Just bear with me here. So we'll look at this first rectangle. If I want it to be inscribed, do I come across at negative 1 or come across at 0? Negative 1. I want it to stay below the curve, so I come across there. There's my first rectangle. Second curve. I want it to be below, so it would be over here, coming from 0. This one I want it to be below, so I come over from 1. And then this one comes over from 2. So depending on the shape of the curve, it will flip back and forth between left-hand rectangles and right-hand rectangles as long as you keep those rectangles below the curve. Those are all the inscribed rectangles then. If we do circumscribed, then I have to be above the curve. There's one, there's the other, and there are the circumscribed rectangles. And then we can go and find the area of each of those rectangles by, again, looking at which side did you count, which side are you going up and coming across. That becomes your f of whatever value. So for instance, the first rectangle here on the left, I would do, the height of that thing would be f of negative 1. The width is what we already determined to be delta x, which would be 1. Then find the area of the other 3, add them all up, you're done. Okay? You're going to have to be able to flip back and forth between left, right, circumscribed, and inscribed. And again, remember, sometimes you'll see upper limit and lower limit used for circumscribed and inscribed. Don't make this more difficult than it is. Just draw a bunch of rectangles, calculate areas. Okay? We'll get into some more theory later on as to how we can get a more accurate answer. We touched on it a little bit, but we'll start looking at limits, like what happens when delta x gets very small or n gets very big. We'll eventually get to a point where we get an exact answer. Okay? And that's actually easier than what we're doing here. But we gotta walk before we run. Okay? Questions? We're good? Pretty easy? Yeah? All right, good. In that case, we're all done. Day 54 tonight. And then tomorrow I'll have the graded integral worksheets for you. We can answer questions on that. And in particular, talk about the differential equations at the back end of that worksheet. Okay? Beautiful.